Good morning. So today I want to explain about the design issues that we face in our design currently lah, which is about static pressure and pressure drop. Yeah, static pressure and pressure drop. So I wanted to explain about this yesterday, but as I wasn't able to explain properly, so now I'll try to explain much properly and much clearly this time. Okay, so as we all know, the fans that we are choosing right now is this fan or this fan because they both have the same specification, and this fan has the rotation speed, maximum rotation speed of 8000 rpm, maximum airflow of 82.79 cfm, and maximum static pressure of 1.09 inch H2O or 271 pascal. And I also showed the graph, the pressure drop versus static pressure versus airflow graph. Okay, so yeah, this is maximum static pressure lah, 271 pascal or 28 millimeter H2O. So at maximum static pressure there is zero airflow, and when at maximum airflow there is zero static pressure. So zero static pressure is when there is no restriction in the airflow lah. So when there is no restriction, when there is no restriction in the airflow, then the fan will rotate at full speed. Okay, so I make some slides here. Okay, I want you guys to pay attention on this. The speed is 8000 rpm, maximum airflow is 82.79 cfm, and maximum static pressure is 271 pascal. And it's also one thing very important for you guys to note, because this is something that I just found out because I just talked to Dr. Chin about this. Okay, this graph that you see here is only applicable when the fan is operating at full speed lah, which is 8000 rpm. So if the fan is operating below 8000 rpm, then this curve will be lower than the red line, will be lower than this line, which is the red line lah. So this red line indicates when the airflow is rotating below 8000 rpm. So yes, it means that the fan won't produce the maximum airflow rate of 82.79 cfm and also 271 pascal. Just giving you an example lah. So meaning to say, if we want the fan to only blow at 40 cfm, which is below 8000 rpm lah, instead of 82.79 cfm, then its maximum static pressure it can produce is much below 271 pascal. Okay, so I'll explain this scenario here. So we will use the scenario when the fan is rotating at 8000 rpm. Okay, so scenario 1, when there is no restriction to airflow. So as the fan is blowing at 8000 rpm, of course its flow rate is 82.79 cfm, and SP means static pressure. So when at maximum airflow rate there is zero static pressure because there's no restriction to airflow, and then the air will continue to flow at maximum flow rate lah, 82.79 cfm, and its static pressure is 0 pascal. So PD means pressure drop. So when there is zero pressure drop, there is zero static pressure. Simple as that. No restriction to airflow. And when there is some restriction to airflow, but then the air can still pass through. So this restriction to airflow is obviously our heat exchanger. Okay, our heat exchanger. So this blue rectangle is the heat exchanger lah. Same scenario. Fan is rotating at 8000 rpm. So maximum airflow 82.79 cfm, and since there's no restriction in airflow, the static pressure is 0 pascal. So as this air enters the heat exchanger at 82.79 cfm, the pressure drop it encounters is 196 pascal. Okay, 196 pascal. And since the pressure drop is 196 pascal, the fan will produce the static pressure which is equal to the pressure drop, which is also 196 pascal. Okay, so since the fan is producing the static pressure of 196 pascal, we look at this graph here. This is scenario 2, right? So 186 Pascal is 20 mm H2O, and this is equal to 22 lah, around 22 or 24 CFM, yeah, around 24 CFM. So yeah, this is what the graph means lah, supposedly, yeah. Okay, I hope you guys understand this lah. Air is flowing at 82.79 CFM, so when it enters this heat exchanger, its pressure drop is 196 Pascal, and because of this pressure drop it encounters, the airflow at the outlet is only 24 CFM, as you can see in this graph here, 24 CFM. Now scenario 3, when there is too much restriction to airflow, it means that the air cannot pass through the heat exchanger. So this is our actual scenario, you know. So like the fan is rotating at 8000 rpm, which means it is going at 82.79 CFM. So when the air is entering the heat exchanger at 82.79 CFM, the pressure drop is around 500 Pascal. And since if you want the air to pass through the heat exchanger, the fan must be able to produce static pressure which is higher than the pressure drop. And because the fan static pressure, maximum static pressure is only 271 Pascal, which is like not able to overcome the pressure drop, then it means that the air at the outlet is only zero CFM. It means like there is no air which is passing through the heat exchanger. And yes, this is our real problem lah with our design right now, because I did a simulation. The simulation is that the air entering the heat exchanger, which means that the inlet volume flow is outdoor air lah, which is 82.79 CFM or 0.0391 meter cube per second. Yeah, and then this pressure drop is 525 Pascal. So yeah lah, this is our main issue we are facing right now. There's no air that can pass through the heat exchanger because this pressure drop is higher than the static pressure, maximum static pressure produced, which is 271 Pascal. And about the issue I raised earlier to Dr. Abdul Karim, what if we reduce the air flow rate to 40 CFM? Okay, 40 CFM. If we reduce the air flow rate to 40 CFM, okay, which is maybe let's say like 3900 rpm, okay, so its pressure drop is 200. Okay, from our simulation result, pressure drop when the air is going at 40 CFM is only 232 Pascal. However, remember that because the fan is not operating at full power, instead of rotating at 8000 rpm, it's only rotating at 3900 rpm. So we cannot expect the fan to produce the same maximum static pressure as 8000 rpm, which is 271 Pascal. So maybe if this fan is only rotating at this kind of power, 3900 rpm, we can only expect like the fan to only produce static pressure of around how much? Maybe like 100, 140 Pascal, 150 Pascal. Yeah, which means that the fan static pressure is still not enough to overcome the pressure drop. So yes, in conclusion, this is our main issue, the main issue of our design. I'm not sure how can we solve it. So I would say like the only solution lah, one solution is we need to increase the spacing between the heat exchanger. We need to increase the gap from the heat exchanger. But then yes, we need to compromise the heat transfer efficiency, maybe to around like 50% or even lower than 50%. So that's all for my concern lah. Yeah, thank you for listening.